some more examples where I compute a left sum, a right sum, and then take the limit of a Riemann sum. And then we'll compute some definite integrals and talk about the first and second fundamental theorems of calculus. So it's all kind of mixed matched. I don't know what's in what section in chapter 5. I just kind of start blabbing, and you guys can get organized based on how it is presented in the book. Do you have anything you want to ask? Anybody? You guys are truly social distancing today. What about you guys at home? Do you have any questions for me? Okay, and here we go. In chapter 6, chapter 5, whatever, we're kind of putting 5 point, I don't know, maybe 5.1 through 5.4 kind of smashed together. We're going to approximate the area under a curve. Using rectangular partitions. And then we're going to expand upon this, and then we're going to use a Riemann sum to get the actual area. And then we're going to use a definite integral. To get the actual area. And we'll make some statements about properties of the definite integral. So that we don't have to use Riemann sums every time. I'd like you to know how to use a Riemann sum. For the same reason I want you to know how to use the definition of the derivative to compute a derivative. Because you can, because that's the historical significance of it, and because you guys are honors students, so you should do a little bit more than the average calculus student. I think we have, today is, what is today? Today is the 12th. So we have a test 1 week from today. It's an in-class test, so you guys at home, I'll have to figure something out. I guess I have to proctor you through Zoom. It's our last in-class test. The date 1 week from today is going to be November. Nope, our test is not 1 week from today. Our test is 1 week from Monday. Nope, it is 1 week from today. I have it filled in my schedule. November 19th. And it looks like the last thing we put on our exam was section 4.2. So it's going to be section 4.3, probably through section 5.4. We'll see how far we get today, maybe. We'll see how far we get today. Come on, you silly thing. There we go. Maybe now you can see it. So I've got to remind you of the formulas that we were using. Here they are. So the Riemann sum has the form has the form of you break up a region and you find the value of f at some particular endpoint in the K partition. So I'm just going to call it xk star. That's going to give the height of the rectangle. We're making the widths all the same. And so that's the product of the height of the rectangle with the width of a rectangle, where we've got some positive function here on the interval from A to B. We cut this up into little increments of size delta x. And suppose here we're at, say, xk plus 1. Somewhere down the line, xk star might be the left endpoint. It might be the right endpoint. We can make it the midpoint. It's just some special x in this rectangle. So in my picture, I'm going to use the right endpoint as my xk star, just to emphasize that I'm forming a rectangle whose height, so here I'm letting this height be f of xk star. That's this length right here. And then this is the delta x. We add those things up from this endpoint to that one. So we start our counter at 1 and go to n. And then this gives us an approximation if we fix n at some number. If we take the limit as n goes to infinity, compute this expression as a function of n, then we get the exact area. In order to compute this exact area, we had to use some formulas. The first one was the sum from k is equal to 1 to n of just 1. Adding n ones together should just give us n. The second one was the sum from k is equal to 1 to n of k. Adding the first k counting numbers together was first plus last, so that was n plus 1 divided by half the number of terms in the list. Then we had one for the sum of the first square terms. This one I always mess up, so let me look it up to make sure I don't mess it up. That's n times n plus 1 times 2n plus 1 all over 6. And there was even one for the sum of the first cubes. I don't know that I'm going to do any ones with cubes, but let me write it down just in case. If I have it. I don't have that one. I don't remember that one. N squared. All right. I would never make you memorize these. I would give them to you. Okay, so you don't need to learn these. That would be hypocritical since I don't have them memorized. I'd like you memorize them. But we might need them. And I've got some examples on a handout here. And this is what we're going to do next. See, back in the old days, back when we could actually mingle with our students, I would pass this handout and we'd work it all together in class. And now I got to stand up here and work it for you. But I'd like you to play along as much as you can. Okay, so Here's the problem. I want you to draw the graph of y is equal to 5x squared plus 2 That's a parabola that opens upward. Kind of exaggerate your graph because we're just looking at the interval from 0 to 1. Then I want you to make 3 subdivisions and compute the sum of the areas of those 3 rectangles. And that is going to be our first approximation. So I'm going to do it on the piece of paper that I have underneath this, because I'm going to write large. Set up a Riemann sum to estimate the area under the graph of y is equal to 5x squared plus 2 between x of 0 and 1 using 3 subdivisions and left endpoints. Draw the graph and the 3 rectangles. Me. I brought my phone case and locked out, and now it's giving me notifications. Okay, so let's keep that separately and let's draw this up here. And out problem number 1. We've got f of x is equal to 5x squared plus 2 from x is 0 to x is 1. And we're going to approximate area with n is equal to 3 rectangles and left endpoints. Let's get that out of the way. So let's make this 1 unit long. My y-axis is going to have probably a different scale. When x is 0, y is 2. When x is 1, y is 7. So it's parabola that opens up. Let's put the point 1, 7 here. And let's put the point 0, 2 here. That's 7. That's 3.5. So 2 might be about right here. Draw you a piece of a parabola in there. Connect this with a vertical line. And now draw 3 rectangles in there. If I'm drawing 3 rectangles in there, then the width of each rectangle in general first is right endpoint minus left endpoint divided by the number of partitions. In our example, B is 1, A is 0, and N is 3. So each of these rectangles are 1/3 of a unit apart. Put one at 1/3, one at 2/3. We'll draw this up here. So you can see I've got 3 rectangles, but I'm going to draw the heights of the rectangle according to the left endpoint. Here in the first rectangle, I make my rectangle look like that. That's rectangle number 1. Left endpoint of the second rectangle is here. And then the third rectangle is here. So you can see our approximation is going to be an underestimate since all of those rectangles are inscribed. So this left sum. Okay, so in the first rectangle, my left endpoint is at 0. And then my delta x is 1/3. In my next rectangle, my left endpoint is 1/3. and my delta x is 1/3. And then finally, my left endpoint on the third rectangle is 2/3, and then 1/3. So what I would written here was the sum of the f at left endpoint times the delta x. Now we got to go get them. We find the values of f at those 3 points by plugging things into here. I already have f of 0 is 2. So my left sum is going to look like 2 times 1/3. F of 1/3, 1/3 squared is 1/9, so I get 5/9 plus 2. Let me just write it like that for now. Times 1/3. And then the next one, I put a 2/3 in here. 2/3 squared is 4/9 times 5 is going to be 20/9 plus 2 times 1/3. I'm going to do what I did before. I'm going to factor the 1/3 out. So let's see, I've got 2 plus 2 plus 2. There's 6. Plus 25/9. 6 is the same as 54/9. 54/9 plus 25/9 is 79/9. Anybody checking my arithmetic? So I'm getting 79/27. And like I said before, this is an underestimate. Because all of my rectangles are inscribed. And so what we're going to do in part 2 is repeat the question with right endpoints. So I'm going to go up here and draw with right endpoints in red. Same 3 rectangles, except for this time the height is given this way. And so this rectangle here is rectangle number 1. The height is given by f of 1/3. Rectangle number 2 is this tall. And then rectangle number 3 is that tall. So this one's going to be an overestimate. Each one of those is exterior to the region. Just too large for me. So my right sum is going to look like f of 1/3, that's the first height, times my delta x, plus f of 2/3 times delta x, plus f of 1 times delta x. And I've already calculated these numbers. I have them up here. F of 1/3 was 5/9 plus 2. F of 2/3 was 20/9 plus 2. I'm going to factor out the 1/3. And f of 1 was 7. So again, I have the 25/9, but I'm adding this time 11 to it. 11 is 99/9. So that's 124/9. Times 1/3. So that's 124 over 27. And this one is an overestimate. To get a better estimate, we would put 6 rectangles in there, maybe 12, maybe more. Keep putting more and more in there until we fill it up. But what we're going to do now is do this thing in general with n rectangles in there. So in the next part, we're going to compute the Riemann sum that gives the exact area under this graph. So let's talk you through the steps here. Part 3. Let's compute Riemann sum that gives the exact area. So our first step is to compute delta x in terms of n. So all we got to do is go back up here and replace the 3 with n. We're going to do n rectangles. So our delta x is b minus a over n. It's going to give me 1 over n. Then second, for x star, let's use the right endpoint. So for the right endpoint, to get to the right endpoint, so here's my interval from 0 to 1. To get to my first right endpoint, I have to take 0 and add delta x. To get to the next right endpoint, I add another delta x to this number. So that's going to be 2 times delta x. And then the next one's 3 times delta x until I get up to the kth one. And that would be k times delta x. So I keep adding delta x a certain number of times to the left endpoint. Since my left endpoint was 0, I'm just adding k multiples of delta x. So my xk star is k times delta x. But delta x was 1 over n. So k divided by n. That's what we have to use as the x value in the function. So the height, we set up the sum of the f of xk star times the delta x from k is equal to 1 to n. Our function was 5x squared plus 2. So we're going to have 5 times my k over n squared plus 2 times the delta x. Goes here. There's my f of xk star. delta x was 1 over n. Does that make sense to you? That's where I'm plugging the numbers in. So now we're going to try to simplify this so that I have a summation on the variable k where we could use our formulas. So I've got to take this and write it as k squared over n squared. So this will be 5k squared over n squared times this 1 over n gives me 5k squared over n cubed. And then I distribute here and get a 2 over n. So what I said it was 5k squared over n cubed plus 2 over n. Now I'm going to write it as two separate summations. These summations involve the variable k. So if there's not a k in there, I'm going to factor the non-k terms out front. So I'm going to take the 5 over n squared out front here. Then I have the summation of all the k squareds. There's not any k's in here, so when I take the 2 over n out, I'm going to leave a 1 behind. We did that because this is where we use our summation formulas. N cubed. Thank you. N cubed right there. Okay, so my summation formulas. For the k squareds, we're going to put in the long expression here, n times n plus 1 times 2n plus 1 over 6. And the sum of 1 is just going to be the n. So we're going to have 5 divided by n cubed. Formula gives me n plus 1, 2n plus 1 over 6. And then I have 2 over n, and this summation just gives me n. We're going to simplify this and then take the limit as n goes to infinity. So we have that the area is whatever this limit gives us. So let's see. I'm going to simplify this last term by canceling the n's. I'm going to simplify this term by canceling one of the n's. Give me an n squared here. And we'll have 5 times n plus 1 times 2n plus 1 divided by n squared times 6 plus 2. You can actually do the arithmetic to compute that limit, do the algebra, or you kind of eyeball it. Remember when n goes to infinity and you've got an expression where the ratio, where the degree on top is the same as the degree on the bottom, the value of this limit is the ratio of the coefficients. So all we have to pay attention to is the coefficients of the n squared. Here, if I multiplied 2n with this n, with that 5, I'm going to get my n squared term. And it's going to have a coefficient of 10 n squared, plus some lower level terms. So 10n squared divided by 6n squared as n goes to infinity is just going to give us the 10 divided by 6. As n goes to infinity, the 2 stays at 2. So I have 5/3 plus 6/3. 5/3 plus 6/3 gives us an actual area of 11/3. It's area, so it's square units. Do you enjoy that? And so guess what we're going to do next? We're going to compute the definite integral and get the same thing. So for problem number 4 in this, let's use the definite integral to compute the area. So on number 4, compute the definite integral. Get the area. So in general, if you've got some positive function bounded above the x-axis between the vertical lines A and B, the area is given by the antiderivative of that function, which we called capital F, and then you evaluate it at those 2 points. That was the first fundamental theorem of calculus. So we're going to put our 5x squared plus 2 here, and our 0 and 1 there. Okay, so let's integrate these. You can hang on to the 5. Just pull it out of the way. This is an x to a power, so we have a power rule for that. Remember, you add 1 to the exponent and divide by the new exponent. So the integral of x squared will give me an x cubed divided by 3. Then we integrate a constant, and we get just that constant times x. Now we're going to get a constant of integration, the plus c, but we don't need it because if I evaluate this, both of the c's will add each other out. So I can just leave that part off. Now I tell myself I have to evaluate that between the 2 endpoints. So I'm going to put the 1 in there for x, and then the 0 in for x, and subtract. But all this stuff in the second batch is 0. 1 cubed is 1. 5/3 plus 2, again, is 5/3 plus 6/3. And there's the same area we got a second ago. Okay? A little bit. A lot of it easier because we've got to be able to do this where I have an x to the 10th power. I don't want to dig up a summation formula for an x to the 10th power and so on. So we'll just do these little tiny examples with parabolas and lines and then worry about how to compute integrals. So I'm going to do this all again. Actually, you're going to do it again. So here I'd like you to attempt these on your own for a bit. This time I've got an upside down parabola, 2x minus x squared. Between x is 0 and x is 2. Draw me this graph of the upside down parabola over that interval. This time break that region into 4 subdivisions, 4 rectangles. Compute the approximate area using left endpoints and then with right endpoints. We'll check our answer together, and then we'll get number 7 started. So let's do problems 5 and 6 real quick on your own. I'm sorry? Zooming in the camera. I'll get these things out of the way. Oops, I zoomed it. F of x is 2x minus x squared. Between x is 0 and x is 2. Where is the vertex of this parabola? Take the derivative real quick and tell me, do this part in your head. Where's the vertex of this parabola? Take the derivative and tell me where its critical point is. At x is 1, right? 2 minus 2x is 0 and 2x is 2, so x is 1. So it's going to go from 0 up to the vertex of 1 and then back down to whatever point it is at 2. Actually, at 2, f is 0, and at 0, f is 0. So you just got that little parabola that goes from 0, and at 1, it's at 1. So you go from 0, 0 to 1, 1 to 2, 0 with a parabola. So I'm going to write this one on here. 0, 0, 1, 1, 2, 0. We want 4 subdivisions. We'll put a point here and here. 0, this would then be at a half, 1, and 3/2. We're going to draw those lines up to here. So for part A, the left endpoints would be 0, 1/2, and 1, and 3/2 as the numbers you plug in to get the height. And for the right endpoints, it's a half, 1, 3/2, and 2 to get the height. Because of the symmetry here, I bet you find that your answer in part 5 is the same as your answer in part 6. One. But that's the same there. All right, I'm gonna catch up with you. For my left endpoint, the first rectangle is gonna have a height of 0. The second rectangle is gonna have a height of 3/4. Let me write that as f of a half. The third rectangle is gonna have a height of 1. And then the fourth rectangle is gonna have another height of 3/4. I'm gonna multiply that by delta x. Each of these is a half a unit apart. F of 0 was 0. F of a half was 3/4. F of 1 was 1. F of 3/2 was also 3/4. So I have 1 plus 6/4 is 1 plus 3/2. So that's 5/2 times 1/2. Is that what you got? 5/4? Anybody? This one's going to work the same way. This one, though, we start here. F of a half plus f of 1 plus f of 3/2 plus f of 2. These numbers we have up here, and f of 2 is going to be 0. So I'm looking at these rectangles. You're going to get the exact same number. So times a half, you're also going to get 5/4. Okay, now we're going to do it in general. So first thing, I'm going to step you through it. Delta x, b minus a over n. What do you get for your delta x? Over n. If we start with the left endpoint and add k multiples of delta x, we're going to call our xk star the left endpoint plus k multiples of delta x. So now do that for this particular problem where our left endpoint is 0 and our delta x is 2 over n. And so you get 2k over n. And now in our Riemann sum, we need to compute the product of f at the xk star times the delta x. So write that out for this particular problem. F of that times our delta x. In this example, f looks like 2x minus x squared. So we've got to put this in for the x a couple of times and then multiply it by our delta x. So for us, it should look like the summation of 2 times 2k over n minus 2k over n squared. That's my f of xk times my delta x. So I want you to simplify that, write that as 2 individual summations, leaving only the k's inside the summation, and then we'll whip out our formulas and our limit. So I'm back at interrupting you. This is going to give us 4k over n. When I distribute this through there, that gives me 8k over n squared. Now the minus sign. When I square all of this, I get 4k squared over n squared. So 4k squared over n squared times 2 over n gives us 8k squared over n cubed. Now we're going to write that as separate summations, pulling out the non-k terms. So we're going to have an 8 over n squared times the summation on k minus 8 over n cubed times the summation on k squared. We're going to use our formulas here. And then we're going to take the limit as k goes to infinity. So the summation, let me pull out the formulas for you. We're going to use this one for the summation on the k. And then we have a summation on the k squared, which is the long one. So this k here, oops, I want that away, go away. I want the formulas, I said. That one is going to be n times n plus 1 all over 2. And then over here, that one is going to be the n plus 1, 2n plus 1 over 6. You take it from there, simplify, and run that limit through there, and then tell me what you get. And then to check if you did the limit correctly, go ahead and jump down to number 8 and compute that definite integral. 2 on here. Where did this 2 come from? Do you get 4/3 each time? 4/3, anybody? All right, let's back up here at the limit. I'm going to cancel with this n with one of these. This 2 goes into here 4 times. And so what I have left out of that is 4 times n plus 1 over n. Nope, this should be an n going to infinity. Over here, I'm going to cancel an n. This is an n squared. 6 and 8 are both even. So I'm going to write a 4, n plus 1, 2n plus 1. And a 3n squared on the bottom. So if you multiply this out, you'd have a 4n plus 4 over n. As n goes to infinity, it's only the n to the first powers that matter. So it's going to give us a 4 here. Here, if I multiply out my n's, I'm going to have a 2n squared times 4 is an 8n squared. Over 3n squared gives me 8/3. 12/3 minus 8/3 is 4/3 of area. And it's always very satisfying to compute the definite integral. We're going to write area as the integral from 0 to 2 of 2x minus x squared with respect to x. Okay, so the antiderivative of 2x is an x squared minus x to the 3rd over 3 from 0 to 2. We put the 2 in first and then the 0. There's my 4 minus 8/3 again. And so we get 4/3 as we did before. You think you can do one of these on your own? I got 1 or 2 of them on your web work. And I'll probably put 1 or 2 on your, put 1 on your test. But let's spend the rest of this time just computing definite integrals by finding antiderivatives. We need to state some of the properties to make sure things all okay. Questions, anybody? Anybody at home? Anybody in here have any questions? Yes, sir. Nope, that's calculus 2. We've got section 5.5 that is integration by substitution to tell us how to integrate composite functions. And then we've got some applications of the integral beyond area, that they compute an average value of a function. We set up a certain thing. We've got a mean value theorem for integrals. So those are 2 things that we'll cover after your test. And then, so chapter 5 is the end of calculus 1. We begin chapter 6 with some more applications of the definite integral. Are y'all taking calculus 2? Are you done with calculus? Done with calculus? You just did this for fun and to meet nice people? You needed an honors class. Yeah, well, we have some biology people. We gotta put up with you for a semester. She's okay though, isn't she? She did okay. Glad to have you. But then you need statistics, right? High school? Oh, so you did the 2300 here? Okay, so let's look at the definite integral. Let's compute a few of them. A definite integral is simply an integral, right? So we have all of the same properties of integrals that we had before. So let me write them down. So if I want to integrate from A to B of a couple of things added together or subtracted, doesn't matter, I can do those one at a time. And if I have constants there, I can pull them out. So let me put a constant here and a constant here. Put that in parentheses. We can integrate the f of x, then tack on that constant, integrate the g of x, and then tack on that constant. So it looks just like the integration rule that we had for indefinite integrals. We can do things term by term through a sum or a difference, just like with a regular integral. Now these represent areas under a curve, where this part here will give us the base, and that's going to give us the height as we sum them up from here to here. So if I want to find the area under a curve, let's see, let's just kind of draw something here. There's A and there's B, and I've got some continuous function in here, and I want this area. Maybe for some reason I want to take a break, find this area first, and that area second, then add them together. You should get the same thing as that area. As a definite integral, it says the integral from A to B of f of x dx is equal to the integral from A to C plus the integral from C to B. This is y is equal to f of x. You can stop at some intermediate points. That's pretty helpful when you have functions which aren't a single piece, but maybe they're piecewise continuous, but there might be a break somewhere that we need to look at. I'll show you an example with that. The next one, if I want to integrate some function from A to B, I find an antiderivative and I plug in the endpoints f of B minus f of A. So what if I go nowhere? What happens if I integrate my function from A to A? Should get 0. It says the area under a single point is 0. Otherwise, we use the fundamental theorem of calculus. And so let's compute some of these. All right, let's look at the integral from 1 to 4 of square root of x dx. So you know you're going to start by writing that as x to the 1/2, right? Now you calculate the antiderivative. Add 1 to the power and divide by the new power. So your antiderivative is going to have a 3/2 power. And then when you divide by 3/2, you flip and multiply. So that's going to put us at 2/3 here. But let me go ahead and write 3/2 here for now. You don't need the plus c because it's a definite integral, but you will have to evaluate that from 1 to 4. So now let me do the flip and multiply step. like that. Okay, so f of b will look like 2/3 times 4 to the 3/2, and f of a is 2/3 times 1 to the 3/2. Well, 1 to any power is 1. So all I have back here is 2/3. Help me out with 4 to the 3/2. What is a 3/2 power? Okay, you can raise it to the 3rd power and then take the square root, or the other order, take the square root, then the 3rd power. It's easier for me to take the square root first. Square root of 4 is 2. 2 cubed is 8. So I have 16/3 minus 2/3 gives me 14/3. Okay, so when your antiderivative is of a function that's above the x-axis, then you can interpret that as area. Let's take the integral from 2 to 5 of, say, four x minus 1 over x squared. Let's start by writing that as 4x minus x to the negative 2. Then we add 1 to the power, divide by the new power. Hang on to the 4, add 1 to the power gives me an x squared, divide by that. Pull out the minus, add 1 to the power, gives me a negative 1, divide by that. And then we don't need the plus c, we'll just go from 2 to 5. A little bit of simplifying allows me to rewrite this as 2x squared. This minus can go with that minus and make that plus. X to the negative 1 is 1 over x. We plug the 5 in for each x and get 2 times 5 squared plus 1 over 5. Then we plug the 2 in for each x and subtract. 2 times 2 squared plus 1 over 2. So let's see what I got here. I got 25 times 2 is 50, plus 1/5, minus 8, minus a half. So let's see, I've got me a 42 here. 1/5 minus a half, that's 2/10 minus 5/10 is minus 3/10. Hey, I can go to decimals then. Let's make this 41.7. I've jumped out of my fraction comfort zone. All right, another one. Let's go with a couple. This is gonna be kind of quick because I'm out of room down here. Let's find the integral from 0 to the natural log of 3 of 6e to the x. All right, integral of e to the x is? It's the integral of e to the x. So the integral of 6e to the x is still 6e to the x. So we have 6 times e to the natural log of 2 minus 6 times e to the 0. What is e to the natural log of 2? Oops, natural log of 3, never mind. E to the natural log of 3 is 3. So I have 6 times 3, e to the 0 is 1. 18 minus 6 is 12. One more, what the heck? Back into focus. Let's find the integral from 0 to pi over 4. So by golly, we're going to do a little trick here. Of cosine of x minus the sine of x. Let's do this term by term. First, the antiderivative. The antiderivative of cosine is sine minus the antiderivative of sine. What's the antiderivative of sine? Negative cosine. So this gives us a plus here from 0 to pi over 4. So we first put the pi over 4 in there. Then we put the 0 in there. Oops, that's a 0. Sine and cosine of pi over 4 are both square root of 2 over 2. Sine of 0 is 0. Cosine of 0 is 1. Add a couple of halves together and you get a whole, and then minus 1. So far, so good? Okay, I'm going to put some other examples up here, but I want to give you an opportunity to take a little break here. This is somewhat halftime. Take a break, stretch your legs, run to the restroom, and I'm going to write down some other examples. You guys at home take a break as well. Anybody at home have any questions? here. Mhm. Well, you guys ready to get back at it? Okay, so when you think about our indefinite integral formulas, all the ones that we had how to find antiderivatives, once we start putting composite functions together, adding rules like absolute value bars and square root signs, we can't just ignore those, go inside and put the bars back on, because they have a geometric interpretation as to what they do to the particular function. I can't just go in here and say that this is the absolute value of x squared over 2 minus 2x, because it's not. Without the absolute value bars, I have the line y is equal to x minus 2. It's a line with positive slope and a y-intercept at -2, right? But when I put the absolute value bars on it, how does that change the graph? If I get this entire line, what does it do? Absolute value takes negative stuff and makes it positive. So the part of this line that's beneath the x-axis is flipped about the x-axis, and that makes this a V-shaped graph. And so when I compute this definite integral, I've got to look at the two pieces of the V. It's not the same equation. So this particular example has a x-intercept when x is 2. When x is 2, y is 0. When x is 2, y is 0. When x is 1, I get the absolute value of -1. So that puts me a point here. So it gives me this piece right there. Now when x is 7, y is 5. And so I have this piece right here. Both pieces are above the x-axis. So the value of this definite integral should be the sum of the areas of these triangles. So here I can write this as the area of this triangle added to the area of this triangle. The area of each triangle is 1/2 base times height. This one has a base width of 1 and a height of 1. The second has a base width of 5 and a height of 5. So I can write the area of this first triangle is 1/2 of 1 times 1. And the second triangle as 1/2 of 5 times 5. So I have 1/2 plus 25 halves. That's 26 halves, or 13 square units of area. So I want you to think of the geometry involved. If you don't think of the geometry, then think of the algebra involved. That the absolute value of x minus 2 looks like itself when x minus 2 is positive, and it looks like the opposite of itself when x minus 2 is negative. And so I can write that as x minus 2 when x is bigger than 2, or equal to, doesn't matter which one has the equal sign. And it looks like 2 minus x, if I distribute this minus sign here, when x is less than 2. And so I can use that linearization rule that says I can find the integral from 1 to 7 by first finding the integral from 1 to 2 of 2 minus x, and then add to it the integral from 2 to 7 of x minus 2. And you should get the same thing. This takes a little bit longer than this geometric interpretation, but you'll get the 13 out of that. The moral of the story is, don't ignore the absolute value bars. They change things for us up in terms of the graph. Don't ignore the square root sign. We've got to figure out what this is describing geometrically, because I can't just go inside the square root sign and say integrate 16 and get 16x, integrate x squared cubed over 3, and then put the square root sign back on. You can't do that with derivatives. You can't do that with antiderivatives. So we're kind of handicapped right now in terms of handling something like that. Draw a picture. What does the graph of y is equal to the square root of 16 minus x squared look like? And then what does it look like between 0 and 4? Does anybody know what this graph looks like? Top part of a circle, right? You square both sides, you get y squared is 16 minus x squared. It's the circle x squared plus y squared is 16. Since I use the square root, I just have the top half of that circle. Centered at the origin of radius 4. But this doesn't want me to find the area under that circle from -4 to 4. It only wants the area from 0 to 4. So this is the area of the quarter circle. Well, the area of a circle is pi r squared. If we only have a quarter of it, I'll multiply it by a fourth. The picture tells me my radius is 4. So I should have 1/4 of pi times 4 squared. Take 1/4 of 4 squared and you'll get 4. This integral has a value of 4 pi. So don't ignore composite functions by ignoring the outside rule. Think about what they mean geometrically. For the next one, I've got some mystery function. Don't know what the function is. Right now, you can't even see the function. There it is. It's some function that when you find the antiderivative from 1 to 4, you get 8. And when you find the integral from 3 to 4, you get 2. Without knowing the function, can you find the integral from 1 to 3? Just kind of make a picture. Just looking up here, if I just use this squiggly line as my graph of y is equal to f of x, and draw an interval from 1 to 4, I know that this total area here is 8 units. Then if I cut this off at 3, draw a vertical line, I know that this area in here is equal to 2. And I'm asked to find this area. And now it's easy. The whole area is 8, and 2 of that area is here. The rest of it has to be here. So what's the rest of it? Six, right? You got 2 here. What number added to 2 gives you 8? That's all there is to it. Okay. Questions? All right, now let's look at the next one. I'm looking now at the integral from 1 to 4, and I have 6 times f of x minus 5. So what I want you to think about is that I can break up integrals around plus and minus signs, and I can pull out constants. So I can rewrite this as 2 integrals that look like 6 times the integral from 1 to 4 of f of x dx minus the integral of 5 from 1 to 4 dx. We don't know f, but we do know the value of the integral without even knowing f. The value of the integral from 1 to 4 is 8. So this gives me 6 times 8. What about this next bit? What's the integral from 1 to 4 of 5? Well, you can find the actual antiderivative of 5, can't you? 5x. Then you evaluate that from 1 to 4. Or you can think of this geometrically. Y is equal to 5 is a horizontal line. I'm finding the area underneath that horizontal line between the 2 vertical lines from 1 to 4. So that's the area of a rectangle whose height is 5 and whose base width is 3. So this should give me 15. Right? Let's just compute the integral though. That gives me 5x from 1 to 4. We have 48 minus 20 minus 5 is that 15 I was talking about. 48 minus 15 is 33. Okay? That's the linearity of a definite integral. All right, part C. Same function. I want to look here. What's the area above that point right here? That's what that's asking. And the answer is 0. All right, I forgot to write one of the properties of the definite integral down for you. Let's see if you know intuitively what it would be. I've integrated this function here from 1 to 4 of f of x dx and got 8. And I want to know what happens if I integrate from 4 to 1. Think about it in terms of a Riemann sum. The numbers here were the a and the b, and the delta x was the difference between b and a. So in this case, my delta x would be 4 minus 1 divided by n. And here it would be 1 minus 4 divided by n. Everything else that happens inside acts the same way. So doesn't it make sense that this integral and this integral have the same value, but opposite in sign? Does that make sense to you? So this should be the same thing as minus the integral from 1 to 4. So this is going to be minus, well, the integral from 1 to 4 I gave you has a value of 8. So add this to the list of your properties. Let's go back over to here for the properties of the definite integral. We've got the linearity property. We've got the, I can break it up into a sum of several integrals, the area above a point, and now one more. Let's add this one to it, that the integral from a to b of f of x dx is the same as the integral from b to a, but opposite in sign. If you reverse the order of integration, or you change the sign of the integral. Okay. You swap these around in any way, it changes the sign. Now we called this step right here, where we find an antiderivative and evaluate the antiderivative at the endpoints and subtract, we called that the first fundamental theorem of calculus. So by gosh, there has to be a second fundamental theorem of calculus. Doesn't have to be a third one, but if there's a first one, there has to be a second one, right? Let's look at the second fundamental theorem of calculus. State the first fundamental theorem of calculus again. This for some function little f with antiderivative capital F. The value of the definite integral from a to b is the value of the antiderivative at b minus the antiderivative at a. Some restrictions are put on this function in that it's got to be nice, right? Can't have a bunch of different breaks in it. Now suppose I have a function like this. Let's take something easy. Let's take 2x plus 1. That's a line, slope of 2 and y-intercept of 1. If I integrate that from 1 to 4, I'm going to get a number that represents the area. But suppose I want to stop somewhere from 1 to t. So I've got this thing here. I've got the area under the graph on the number line from x is 1 to x is t. Well, it depends on what t is, right? I mean, especially if t is to the right of 1 or to the left of 1. Now I've got an antiderivative. I'm going to evaluate it at t and evaluate it at 1. So I'm going to get the antiderivative as a function of t. Now suppose I say, take the derivative of that thing. This is going to give you some version of the antiderivative at t minus the antiderivative at 1. But it's a function of t. So now I'm going to ask you to do this. After you calculate that, take the derivative of it with respect to t. Okay, so I'm going to go over here and I'm going to take the derivative of this with respect to t. And I'm going to get f prime of t, capital F prime of t, minus 0. Because the antiderivative at 1 is a constant. But this capital F was the antiderivative of little f. So I should get little f back, but now as a function of t. So in this particular example, we should get 2t plus 1. And we will. It says that this operation, differentiation, and this operation, when done as a function of a variable, undo each other. And you end up with what you started with as a function of this variable. So it says this. Says that the operations of integration and differentiation are inverses of one another. The derivative of an integral gives you the function back, just like the integral of the derivative generates the original function. It says that the integral, say, from a, let me do it as a function of x this time, and put some function of t in here, has a value that's a function value of x. The derivative of that function of x is the integrand as a function of x. No plus c. The derivative of an integral gives you the integrand. Even if you can't compute it. Here we can compute it. I can get x squared plus x. So when I put this in there, I get t squared plus t. The derivative of t squared plus t is 2t plus 1. But if this is something I can't compute, and I want to take the derivative of an integral, these two operations kill each other. We get this function back, but as a function of the upper limit. So for example, let's find the integral of the sine of t to the fifth. Well, you would think that the integral of sine of t to the fifth be cosine of t to the fifth, but it's not. Because the derivative of cosine of t to the fifth does not give you sine of t to the fifth. The derivative of cosine of t to the fifth gives you minus the sine of t to the fifth times 5t to the fourth. So I don't know the antiderivative of this. But suppose I want to compute it as a function of x. Now I have an antiderivative as a function of x. And I want you to take the derivative of it. I can. So if I want you to find the derivative of the integral from 0 to x of the sine of t to the fifth dx, it's a quickie. What is it? It's just the sine of x to the fifth. Okay, there's no, I don't worry about that being a t to the fifth. I just get whatever the antiderivative is, evaluate it this, and then take the derivative, gives you the function back. The chain rule version of this looks like this. Chain rule version of the second fundamental theorem of calculus. Says that if this upper limit here is a function of x, then the derivative with respect to x of an integral where the upper limit is a function of x, and this is some function of t in here, gives you the composite. The derivative still kills the integral, gives you this as a composite function of this. And now the chain rule part says now you multiply by the derivative of that. And so, for instance, page 9 here. That of x be the integral from 10 to the square root of x of the cosecant of t divided by t squared plus 1 dt. Find f prime at t. So I define f to be this version of an improper of a proper integral, definite integral, and its square root of x of that funky looking expression, cosecant of t divided by t squared 1. So if I'm asking you to take the derivative of something that is an integral, you should get the integrand back. And we will. We're going to take the derivative of this, that kills that, gives me the cosecant of the square root of x divided by the square root of x squared plus 1. But then the chain rule part says multiply by the derivative of the square root of x. Derivative in the integral are inverse operations. Okay. All right, and so your third test goes through here. That I said was 1 week from today. So let's get organized at what we're going to put on this test, and then I'll talk about let's get organized, meaning we get organized. Starts with section 4.3. Now let me see if I can remember what was in these sections. In section 4.3, we did all that stuff with the first derivative. Took the first derivative, we set equals 0, we got critical numbers, and the first derivative told us where the graph was rising and falling. Then we expanded that further and used the second derivative to tell us where the graph was concave up and concave down. So we had what the first derivative and the second derivative tells us about the graph. So find critical numbers, find inflection points, tell me where it's increasing, decreasing, concave up, concave down, relative max, relative min. In section 4.4, I forgot what we did. I think we did more complicated things where we have, no, I don't know. I'll have to peek. I don't remember what we did in section 4.4. We did funkier functions. Functions that had horizontal asymptotes, vertical asymptotes, and cusps, and vertical tangent lines. In section 4.5, we learned more about taking limits, especially those of the form 0 over 0 or infinity over infinity. We did that with L'Hopital's rule. And then make sure you look at the limits of other indeterminate forms, especially the kind where we took use the logarithm to help us take limits of the exponential indeterminate form. Section 4.6, we did the applications of the derivative to optimization. These were our optimization word problems. Chapter 5 was all kind of running together for me, but these first 3 sections dealt with finding a, the first one was just general antiderivatives. So you got a list of formulas that hopefully you all know by now. Sections 5.2 and 5.3 involved computing approximate areas with a left sum and a right sum, and then in 5.3 with a Riemann sum. Okay, so left and right sums. And then here was a Riemann sum. And then in section 5.4, we've got the definite integral. Okay. I will put a review sheet on Blackboard. So I want you to review this over the weekend. And then let me tell you about the rest of the semester. Today is November 12th. On November 17th, which is a Tuesday, we'll review for your test. And if we need some more time, maybe we'll work on 5.5. I'm going to do an example on 5.5 today. November 19th is your in-class exam. Then we have our Thanksgiving week on the 24th is a Tuesday. That's our last in-class day. We'll do section 5.5 in class. Then on the 26th is Thanksgiving. And December 1st is the last day. We will meet through Zoom. So I do need to cover more than 5.5. So last class day. I'm gonna do some 5.5 today. 5.6 is the last of them. The last day we meet through Zoom. December 3 is the study day. Is December 8th. Scheduled for 10:30 a.m. to 1 p.m. And we will discuss this final exam right here, but you're going to be taking it at home. So what we'll probably do is Zoom. I'll send you an exam through the mail, and you'll take the exam at home while I watch you do it on Zoom. Have I got a camera on your computer at home? Sound good? All right, so looks like I want to make sure we spend a lot of time on section 5.5. 5.6 is short, 2 little formulas, but section 5.5 is really super important. So I want to mention a little bit of that right now. Section 5.5, we're going to use a method of substitution to help us compute integrals, both definite and indefinite integrals of composite functions. So when we learned how to take derivatives of composite functions, for example, if I wanted to take a function like x squared plus 9 and then raise it to another power, the derivative of that was more than just bringing the power down, raising it to 1 power less. You had to multiply by the derivative of what's inside. And so we can simplify that to something like 10x times x squared plus 9 to the 4th. That means that if we're going to take the antiderivative of this, we should get that. The antiderivative of 10x times x squared plus 9 to the 4th should give us x squared plus 9 to the 5th. So I've got like a product in here. I've got an x outside the parentheses, I've got an x inside the parentheses. If you have such a product, you have to do more than just add 1 to the power and then divide by the new power. Well, if I divide here by 5, let's divide both sides by 5 so that it looks like that. And that says 1/5 times x squared plus 9 to the 5th comes from the integral of 2x times x squared plus 9 to the 4th. So I needed more in here than just the x squared plus 9 to the 4th, where it looks like I'd raise 1 to the power and divide by the new power. I need this extra term here. And that extra term has to play the role of the derivative of what's inside. If I have that kind of setup, then I can compute the integral by adding 1 to the power and dividing by the new power. And that would give me my antiderivative in general if I tack on the plus c. That's true this way as well. Suppose I want to take the derivative with respect to x of a logarithm of something. Say the natural log of x squared plus 2x plus 7. The derivative A logarithm of something is found by going 1 over u times u prime. So it's 1 over x squared plus 2x plus 7 times my u prime is 2x plus 2. So if I want to go backwards, if I want to integrate x squared plus 2x plus 7 with the 2x plus 2 up here, undo that derivative, I should get the natural log. So I need more than just the u. I need the u prime as part of the integral. If I have the u term and the u prime term as part of the integral, then I can undo it with a power rule and with a logarithm. So if we have integrals of the form, suppose we have some sort of function of u in here, so let's call it f of u, and then we have u prime of x times dx. If we have that, then we just find the antiderivative of f as a function of u. We need the derivative of whatever the compounded part as part of the integral. This drives me nuts. Probably drives you more nuts than it drives me nuts. If we have integrals where we have a composite function times the derivative of the stuff inside, then we just find the antiderivative of the composite function using whatever rule we have. Power rule, 1 over u, e to the u, sine of u, cosine of u, and so on. So we're going to call this integration by substitution. I'm going to take the composite part and call it u, and then I've got to see if my outside part corresponds to the differential of u, which is u prime times dx. So sometimes I call it a u du substitution. Let me show you how it works. We'll do an easy example. Let's take the integral of something to the 10th power. Let's just go 4x plus 3 to the 10th power. The question is, what did I take the derivative of to get 4x plus 3 to the 10th? Well, if it ended up with the 10th power up there, I had to have, before I took the derivative of it, I had to have an 11. So this should be some version of 4x plus 3 to the 11. But the derivative of 4x plus 3 to the 11 is more than just this. So let's kind of think our way through it. I'm going to try to treat this as an integral of u to the 10th times this part, du. In order to do that, I got to substitute both of these guys out. I have to substitute out the 4x plus 3, and I have to substitute out the dx term. I'm going to do it like this. I'm going to take the stuff inside the parentheses, and I'm going to call it u. Now in the chain rule, we have to take the derivative of that. So let's do that. The derivative of u with respect to x, in this case, is 4. I'm going to break this up as a fraction where the differential of u divided by the differential of x and solve for the differential of u like this. Okay, now I don't have a 4 in front of this dx. I do have a 4 here. So I'm going to take care of that by solving this equation now for dx. That du over 4 is dx. Now where I have this, I'm going to put in u, and where I have dx, I'm going to put in du over 4. So I have a u to the 10th times du over 4. That 4 looks goofy right there. Let's pull it way out front as a 1/4. We made a composite function integral look like a single variable integral, simply by putting a 1/4 du in there. And now I can integrate it as a single variable. Add 1 to the power, divide by the new power. So I have a 1/4 u to the 11th over 11. And I'm done, so I tack on the plus c. Not quite done. I need to put my original expression of x back in where the u is. So I'm going to have u to the 11th over 44, but u is 4x plus 3. That's the function whose derivative is this. And if you do take the derivative of the 4x plus 3 to the 11th over 44, bring the 11 down, cancels and gives me a 4 on the bottom. 1 power less gives me the 10th. The derivative inside wipes out the 4 from the bottom. Okay. So what we're going to try to do is make all of our integrals that we had before into their most general form. Take our x to the n rule dx and write it as a u to the n du. Our 1 over u, e to the u, sine of u, all of those integrals, we're going to go and rewrite them. So we're going to try to write general integrals of the form, well, u to the n du, u to the -1 or 1 over u du, e to the u du. What were some of the other ones we knew? Sine of u, cosine of u, secant squared of u. What else do we have? Secant of u, tangent of u. Cosecant of u, cotangent of u, cosecant squared of u, and then our inverse trig functions. 1 over u squared plus 1, 1 over the square root of 1 minus u squared, and 1 over u square root of u squared minus 1. Those are the known integrals. I'll work my way backwards. This one would be an inverse secant of u. The one up here is an inverse sine of u. And then this one up here is an arctangent of u. The function whose derivative has a cosecant squared in it was a cotangent, but it'd be minus the cotangent of u. The function that has a cosecant cotangent in it is a cosecant, but it'd be a minus the cosecant of u. The function who has that as its derivative is a secant of u. Secant squared comes from taking the derivative of a tangent. Cosine comes from taking the derivative of a sine. Sine comes from the derivative of a minus cosine. Derivative of e gives you e, so the integral of e will give you an e. This one was the natural log. And this one was our power rule. The only thing is this little symbol here, du, is the derivative of the u times the dx. In each of these, u is some function of x, and the du is u prime of x times dx. The derivative of whatever's inside has to be written out here or be off by at most a constant. If it's off by just a constant, we can manipulate that. But otherwise, I need this function to have its derivative as part of the integrand. And then we can trick these into being all the basic integrals that we had before. Like, for instance, suppose I want to take the integral of e to the 6 times x. Well, just from what you know about exponential functions, you know there has to be an e to the 6x in here somewhere. Right? But the antiderivative of e to the 6x is more than e to the 6x. Gosh, you stupid thing. If I just went over here and say that that's e to the 6x, I'm going to be off. By how much? What's the derivative of e to the 6x? It's e to the 6x times 6. So I would have a times 6 that I need to take care of. Well, my antiderivative then should have a divided by 6. Well, let me show you. Let me try to make it look just like the e to the u du integral. I'm going to take u just to be the exponent. Then I take the derivative. The derivative of u with respect to x gives me a 6. So that the derivative of u is 6 times the derivative of x. Okay, so I don't have the 6 in here. So I want to get it out of here by moving it over here with the du. And now I make 2 substitutions. Where the 6x is, I put in a u. Where the dx is, I put in 1/6 of du. So that says I've got the e to the u du integral with this extra constant. As long as it's just a constant, I can pull it out front. Now it's a single variable. The integral of e to the u is e to the u. And so I get 1/6 e to the u plus c. So you trick it into being a basic integral in terms of our new variable. You compute the antiderivative in terms of the new variable. And then in the end, replace the composite part. Like that. Okay. I got time for another one. Crazy how it gets blurry on me. You're going to teach yourself how to read these. All right, I've got a product. I can't integrate a product term by term. So I have to think of my product as a function with an inside times the derivative of the inside, like the chain rule. So my function here is the sine. The inside is the x cubed. The x squared dx is some version of the derivative of the inside, give or take a constant. So we find that constant by, let me rearrange this now. Let me put the main part of the function here, and let me move the x squared next to the dx, because that's going to be the derivative of the inside. Now do the formal substitution. I'm going to replace u with the what I'm calling the inside. Then I'm going to take the derivative of that. Instead of writing now that as du dx and then multiplying by dx, I'm just going to go ahead and do that step. The derivative of u will be the derivative of this times the dx. And when I compare it with this, I've got that, but without the 3. So I'm going to take this line and solve it for x squared dx by moving the 3 over here as a 1/3. And now I'm going to rewrite it. This becomes the sine of u, and x squared dx is 1/3 times du. If there's just a constant to factor out, you can do it. So I've tricked this product into being this fundamental integral. The integral of the sine of u was the one that was minus the cosine of u. When you've got the antiderivative, you tack on the plus c. But one additional step is to replace the u back with the x cubed. And then always do a mental check. If I take the derivative of this expression here, am I going to get all of this? Well, the derivative of a cosine of x cubed gives me minus the sine of x cubed times the derivative of x cubed. And the derivative of x cubed is 3x squared. Multiply that by the negative 1/3. It takes care of the 3 and the minus sign. And sure enough, I have the same thing down. Okay? How many of you have done stuff like this before? Do you do it like this, or do you do some version of this? I mean, if you've got a way that you're set in doing it, I can understand, I can work my way around that. You don't have to do it exactly the way I do. All right, we're going to do a boatload of examples of these. What I want you to do is get yourselves ready to do well on this third test, and then we're going to become masters at this integration by substitution. Good? All right, thank you, everybody, including y'all at home. Hope to see you here soon. Thanks for that. Anybody have a question at home, or I'm gonna cut this off unless you have any questions? Anybody at home have any questions?
So I still need to take that first exam.
Did you decide on when you wanted to do it?
Could I do it like that Tuesday before Thanksgiving?
You can. You can. Find a day and find a time of that day, and we can figure that out.
What like time ranges?
This is my only activity on Tuesday, so after this class, I suppose.
Okay.
Good?
What time works?
Okie doke. Thank you. You're still with me here. You guys have any questions, or are you just logging off? Yeah? All right, I'm cutting everybody off then.